Variation of power of lens with the wavelength of light. We know lens makers formula, okay, 1 by f, that is 1 by focal length, equals mu minus 1 bracket 1 by r1 minus 1 by r2. Let us call it equation 1, okay. And for a given lens r1 and r2, okay, are constant. R1 and R2 are radius of curvature of two spherical surfaces of the lens. And since the lens is solid, so R1 and R2 are constant. Okay. And refractive index, okay, refractive index mu depends on wavelength, okay, lambda of light, okay, light, as mu equals a plus b by lambda square plus c by lambda power 4 plus dot dot so on. So this relation gives the dependence of refractive index, okay, with the wavelength of light, and a, b, c, okay, are constant. So this is to be noted. Now what we find, if lambda, okay, increases, then refractive index decreases, okay. So if it increases, then refractive index decreases, and if lambda decreases, okay, if it decreases, then refractive index increases. So we find this, okay, from this relation. Now from 1 and 2, okay, we can write power P of the lens P equals 1 by f, and from 1 and 2, okay, since R1 and R2 are constant, so this quantity inside the bracket, okay, is constant. So we can write power P proportional to or depends on mu minus 1. So we find this. Sorry. Now what we get, okay, looking into this expression. So if wavelength increases, okay, then refractive index, okay, decreases, then power, okay, decreases. So power decreases if wavelength increases, and if wavelength decreases, okay, I'm putting down arrow, if it decreases, then refractive index increases, therefore power increases. So we find this, okay. So if we plot the graph between power and wavelength, then the graph is of such nature. So this is the nature of graph, okay, or variation of power with the wavelength of light.